Hi, in this presentation we're going to talk about hypothesis testing. So where would hypothesis testing be useful? Here's an example. Let's say you're a shop owner and you have one employee, and at some point this employee comes to you and says, she usually takes care of the store in the mornings. She tells you, I don't think I should be coming in from 9 a.m. to 10 a.m. every day because there's only 2 customers on average that I see there. And I don't think I really don't think I should be coming in. It's not economically viable. Then you take a step back and you don't want to take this at face value. So you think a little bit and you decide you want to test this. You want to see if your employee just doesn't want to get up in the mornings, or if she's actually right. If there is 2 customers on average there every morning, and subsequently you shouldn't be doing this. You shouldn't have your store open during these hours. So how do we test this? So first of all, we think about this and we come up with a stochastic model. So here's our model. You're going to observe your number of customers starting from tomorrow for a couple of days, let's say n days, and you call the number you see between 9 and 10 a.m. x1 up to xn. And let's say that you think those numbers follow a Poisson distribution with parameter lambda, where lambda is larger than 0. Now, this is clearly some assumption we're putting on the number of customers, but Poisson distribution is usually a good choice for things like how many customers do I see in a specific time period. And let's also assume that those customer numbers are IID. Now, this is a strong assumption in some sense. In practice, you can clearly say that on some days you'll probably see more customers because there's a sports event or because it's the weekend. But for the sake of this recitation and for simplicity, let's just go with an IID assumption. OK, and now you collect all this data, and then what you want to do is you want to make a decision. Namely, and I'm going to call this number 1 because we'll see some different setups. We are going to go through 3 different setups for hypotheses in this recitation. So you want to make a decision between you believe your employee and you think that lambda corresponding, because the expectation of a Poisson distribution is exactly lambda. Lambda equals 2 corresponds to 2 customers on average during this time period. And you have an alternative hypothesis. Lambda is not equal to 2. And so essentially, you want to collect enough evidence to say, I think that h1 is true. I do not think that h0 is true. But there is also uncertainty, so you're going to make some errors. So first of all, our goal is to find a test. And the test is going to be a function psi that depends on all your data points. And that is a number either 0 or 1. Corresponding to one of these 2 hypotheses. Yeah, and we want something from this test, but what we actually want, I'll tell you in a bit when we talk a little bit about errors. So let's briefly review the types of errors you could make. So whenever I see data and I have 2 options, h0 and h1, and I decide for one of them, there's the possibility that I do something wrong. So, and we classify the error that we can make into 2 types, type 1 error and type 2 error. Type 1 error is the one that I make when actually h0 is true, but I think it's not. So let's denote this by alpha subscript psi for the test, because this depends on the decision, how we make our decision. And let's also let this depend on lambda, on the underlying parameter. It might vary depending on your setup. And this is the probability. If lambda is true, and lambda is in theta 0, which is the associated set, the set associated to the null hypothesis. So in this case, this would just be all the parameters in the null hypothesis, which is just the number 2. And similarly, we have theta 1, which is all positive numbers except for the number 2. OK, so if I have lambda in theta 0, then this is the probability that my decision rejects the null hypothesis. That is the probability that I say I do not think H0 is true, while in fact it is. And conversely, we have type 2 errors. Denoted by beta lambda, beta subscript psi lambda, which is the probability that I accept the null hypothesis, that I think, OK, given what I've seen, I think the null hypothesis is true, if in fact it is not. If in fact the alternative hypothesis is true. And then you've already seen in class there's also a thing called power, which is defined as 1 minus the type 2 error. So those two are exchangeable. It's just that, yeah, we want beta to be small, and we want the power to be large. OK. So, and clearly, those two are complementary. So here is an example for a test that has very low type 2 error. Let's always output that I think that the null hypothesis is correct. Let's never reject the null hypothesis. Then this can never occur, so it's great. My type 1 error is 0. The problem is my type 2 error will be 1. Whenever I actually see lambda in the alternative hypothesis, then I'll always be outputting 0. So this is always 1. And this is not a good choice intuitively. So we always want to strike a balance between these two. Right. And usually this balance is achieved in a somewhat asymmetric way. Namely, we always favor type 1 errors in some sense. Usually, when we're asked to produce a test, this test will come with a certain level. And level is the amount of uncertainty that we tolerate for our type 1 error. So we handle these two hypotheses asymmetrically. We say that we want to be really certain about what we're doing when we reject H0, when we say that H1 is correct. We want to be really certain that, given the data we've seen, we can with confidence say that H0 is probably not correct. Of course, whenever we do this, we are going to make some type 2 error. But depending on what the actual underlying lambda is, if it's actually in the alternative hypothesis, this might not be too bad. OK, so the level of a test is the biggest number, essentially the biggest type 1 error that I see within all lambdas corresponding to the null hypothesis. So that is, what's the probability that I reject the null hypothesis, that I say the alternative hypothesis is true? We call this alpha. And this is the supremum, so the biggest type 1 error that we can make. And when you're asked to produce a test with a certain level, often what we really want is just that alpha is the biggest error that you can tolerate. But when we asked you to produce a test in homework, for example, what we actually want is we want you to find one that has exactly the supremum equal to alpha, just so we actually fix the error level. But usually, it's just defined as being better than alpha. OK, so and often this could be hard to achieve. It could be hard to exactly find a test that exactly yields something like this. And one way of getting around this problem is to, so the problem here is we would actually always have to understand the distribution of any test statistic we come up with. And one way to simplify our life a little bit is to say that maybe we only know the asymptotic distribution of our decision psi. And this is what we call an asymptotic level when we put a lim sup here as n goes to infinity. So that means, so lim sup just means I again have something like a supremum here. If you want, you can just think about this as a limit. So as n goes to infinity, how big is my type 1 error going to be? I don't care about what happens for finite n, just how big is the limit. And this often simplifies calculations. But of course, the downside is for fixed n, because in practice you will never have infinite data, you will always have only a finite number of samples, only arguing asymptotically can be a disadvantage. Because this wants to produce a certain level of certainty, and you cannot be 100% certain if all you have is asymptotic descriptions of what you're doing. OK, and let me briefly write down what I said before, namely that there is an asymmetry here. We can actually, although we often say we accept or reject the null hypothesis, we can only really ever reject the null hypothesis. We can only reject or refute H0, never accepted. So why is this? Because essentially, if we want to be really certain, so what's a common level of alpha? Let's say alpha is 5%. If we want to be really certain about this, then often for values close to the true or to any lambda in theta 0, we'll have a very large type 2 error. So we can never be certain that if we see something in that looks like H0, we can never be certain about our decision. Our guarantees will often be quite weak whenever our decision actually outputs 0. But when it outputs 1, then by fixing a certain level, we have a certain kind of security or a certain kind of certainty that what we are outputting actually matches data that convinces you that H0 is not true. So in the example that I gave you with the store owner, the store owner can really try and reject H0 and gather enough evidence to say, no, what my employee said is probably wrong. But if the test then outputs that H0 is true, then that just means there's not enough data to actually say that what she was saying is wrong. OK, so next, I'm going to try and derive some asymptotic tests. So let's change our goal to actually ask for asymptotic level alpha. And let's try to produce a test for this kind of hypotheses. And the strategy of how to produce this is often similar. Namely, our strategy is first to find a pivot or a test statistic. Tn. So what's a test statistic? A test statistic should be something that basically measures the distance between what kind of parameter lambda does my data suggest and what kind of lambda corresponds to the null hypothesis. So and if those two look very different, then I would like to reject. And if those two look similar, then I would probably go with H0. And it's also called a pivot, or it is a pivot, if I can manage to write it down in such a way that its distribution does not or such that its distribution under the null hypothesis is known and does not depend on any additional parameters. So, and in that case, I have an easier time fixing the level of the test, writing down the level of the test. And once I have this, then think about this as some kind of distance function, and then my test statistic is just an indicator function of does my test statistic exceed a certain threshold S. And then in a second step, that is hopefully guided by the distribution we found for Tn in step A, we determine S to match the level alpha. All right, so let's tackle this in this example, but first I have to erase the board.